Seemed a bit quiet this morning. Anyway, good morning. Hello. It's a Sunday, 10 o'clock in the morning, so it's time for our physics tutorial. Oh, a name I don't recognise yet. Good morning. Is this lesson today for GCSE or more for A-level? It's more for A-level today, but I'm going to go through everything pretty slowly, so GCSE students can certainly keep up, and it's a lovely primer for what you've got to look forward to in the future as well. But no, this is going to be mostly A-level content. And who is this? This is Jackson as well. Jackson, Freya, and Lavina, sorry. So hello, good morning, Puddle-Uddle. Everyone's there. If you haven't yet done so, if you could please join the Spiral class. I'll just put the link into chat there. Hi, Tilly. Good to see you. I'm going to be asking some questions in the second half of today, and it's your chance to put answers in and see how well you're getting on using Spiral. If you've never used it before, you don't have to register. You just type your name, and then you can go ahead and start putting your answers in as and when. If you want to click the link, it's in the description. It's also in the chat, which I think is there on my screen. Today we're going to do a practical. Sort of. I mean, we can't really do practicals through the internet, but we're going to do some sort of practicals. Wombat, maybe I'll have a look at that later. Sorry, we're finishing off a conversation from before the video started. No, we're going to do a practical of sorts, looking at the one quantum phenomenon that I haven't yet mentioned in these tutorial sessions, which is the photoelectric effect. Then we're going to look at some questions that students find challenging. I'm not sure why they find them challenging, these mathematics questions, because they, I think, are quite straightforward. You're just applying an equation, but students do, in my experience, struggle with it. So that's what we're going to look at in the second half, and I've made a special drill spreadsheet. That's a question generator that you can use to practice that skill. And if you've never seen my question generators before, you might find them helpful. They are freely available to regular participants of these tuition sessions. Details for how to get to them, either send me a message, maybe drop it in the comments below, but it's in the description of the tutorial here. So the practical I'm going to do is the photoelectric effect. We've already had a little look at the excitation, de-excitation in the last tutorial session, where we introduced the energy of the photon, E equals hf. In today's session, we're going to look at a particular phenomenon called the photoelectric effect that can only be explained if we consider light to be transmitted in discrete packets of energy rather than a continuous wave of energy that's absorbed by surfaces. If instead we consider light to be transmitted as packets of energy, discrete packets of energy, then we can explain this phenomenon that we're about to go through today. This was a big moment. 1905, Albert Einstein wrote, I think it was 4 papers in total. I might be wrong with that, it might be more than that. But certainly he wrote about the photoelectric effect, and it was his miracle year of papers, 1905. And the photoelectric effect shifted. Yeah, and I know zany pictures. I was thinking about it last night, Wombat, and I realised I spent about 3 hours trying to find zany pictures to put in, and I decided not to. So I'm sorry there are no zany pictures this year, but if you've got this week, but if you've got a preference, maybe you've got a theme that you'd like some zany pictures next time, drop it in the comments and I'll see what I can do. So we're going to use a piece of software simulation that's made by the Virtual Physics Laboratory. And I've used those before because the Virtual Physics Laboratory gave me permission to use their simulations. If you don't know about the Virtual Physics Laboratory, well, I think so, Wombat, yeah. No, if you don't know about the Virtual Physical Laboratory, they are responsible for things like holding the British kilogram and using that to calibrate all other balances, which then are used to calibrate other balances and so on. They calibrate thermometers. They basically decide what units of measurement are in practical terms. I know we've got the SI definitions, but to practically calibrate instruments, that's what the National Physical Laboratory does, amongst other things. And one of the teams at the National Physical Laboratory has a chap called Dr. John Nunn, who's written a suite of simulations that schools are allowed to use. The license for them says that schools are allowed to use them for free. Teachers are allowed to use them for free as long as they've attended a training course, which I have done. And students can use them, but it comes at a fee. So I asked Dr. John Nunn for permission to show the simulations with these tutorials. Yes, the first one was wombat. Yeah, absolutely, the first one. And then there were many, I mean, the prototype kilogram. Then there were many copies of that, copies of copies of copies, and so on. And practically, that's what we still use when calibrating instruments. But anyway, that's a digression, really. That's just me talking about the National Physical Laboratory, who've made this available for free. So if you're interested in getting a license for these sorts of simulations to use yourself, this is not a paid-for promotion. But if you go onto the internet, look up National Physical Laboratory Virtual Physics Lab, VPL, you'll find the suite of simulations there, and you can get a license for them. So in this practical, what we've got, let's have a look at this. We've got a lamp. A lamp I can change the brightness of. It's connected to a power supply with a variable potential difference across it. Fine, okay. Then there's a filter. And this filter is going to allow only one wavelength of light, monochromatic light, to pass through it. And here's my ability to select different filters. And you can see each filter has a different wavelength of light that it allows to transmit. And I hope that those numbers you can read. I'm not sure if they're coming through clearly enough, but I really hope they are. So that's fine. So we've got light going down here. Then we've got this piece of metal here. And I can change what that metal is. And it's got two arbitrary metals, just 1 and 2 here. But I've got some piece of metal. Now what happens is when the light hits this metal, it can cause electrons to leave the surface of the metal. According to the wave theory of light, light energy is transmitted in these waves. And if you wanted to get electrons to have enough energy to leave the metal surface, you just have to have a bright enough light shining on them. Because according to the wave theory, the brighter the light, the more energy there is in the light. Very straightforward theory, and it makes a lot of sense. But what was observed was that you could not get electrons to leave this surface at all. You could not get electrons to leave this surface at all with certain colors of light. And the way we can check that is by connecting this metal surface to a very sensitive ammeter, a picoammeter. This picoammeter here will measure the current. It will measure the rate of flow of charge. If electrons are able to leave this surface, we would detect a flow of charge and the rate of flow of charge on the picoammeter. And here is the display on the picoammeter there. And you can see that no matter how bright the light is, if it's red light that's hitting that surface of metal here, which is coloured a browny colour here, then there's going to be no current. No current whatsoever. That is what it is. Now, wave theory says that shouldn't be the case. A brighter light, I should get a charge coming off. Now, this metal grid, which is represented with the white dotted line above here, this metal grid is there to complete the circuit. When electrons leave the metal, what we need to do is conduct them back around. Once they've left that metal surface would then be charged, which would attract those charges back. So really, we want somewhere else for those charges to go. And that's what that metal grid does, so that we have this flow of charge. Now, if I use a filter, an orange filter, you'll see there's some current. So this particular metal, when orange light is incident on this particular metal, a wavelength of 580, I think it says 580 nanometers, photoelectrons, that's what we call electrons that come off of the surface because of light. It's not a special type of electron, it's just a name for electrons that come off the surface because of light. Photoelectrons can be emitted with 580 nanometers for this particular metal. But red light, so 630 nanometers, no photoelectrons are emitted. And that's interesting. That's something that deserved an explanation, and the wave theory couldn't explain that. So Albert Einstein proposed this, proposed applying this idea of quantized energy, which was already around. Max Planck already came up with that idea, but he applied it to light, packets of light energy, which we now call photons. A very successful theory. If I change the metal to a different metal, you'll see that even orange light isn't able to get the current to flow. And if I switch it up to yellow, even yellow light isn't able to get the current to flow. Green light just about manages it. So it turns out for different metals, there are different wavelengths of light that allow the photoelectrons to leave the surface. You know from the wave equation that wavelength is inversely proportional to frequency. So I'll write that equation down. If you're a GCSE student, this is one of the equations you are expected to learn. Wave speed is equal to frequency multiplied by wavelength, which means as the wavelength increases, the wave frequency decreases. And what we say is there is a threshold frequency. We could refer to a threshold wavelength, but we more commonly refer to a threshold frequency. Let's move this to the side. A threshold frequency for electromagnetic radiation, above which we get photoelectronic emission, below which we don't. Some threshold frequency. Now, according to Einstein, the energy of a photon is equal to Planck's constant multiplied by the frequency of the electromagnetic radiation. I think we saw that in the last session. Planck's constant, just as a reminder, this is from memory, so someone correct me if I'm wrong, 6.63 times 10 to the negative 34 joule seconds. So you see the energy of the photon is directly proportional to the frequency of the electromagnetic radiation. That's why we use threshold frequency rather than threshold wavelength more often. Because if you increase the energy of the photons, the packets of electromagnetic energy, by increasing the frequency of the electromagnetic radiation, then when you have a high enough frequency, a low enough wavelength, then photoelectrons can be emitted. Okay, so there's a name for that amount of energy, that critical amount of energy, where above it, photoelectrons can be emitted from the surface, but below it, they can't. I'm going to call F0 here the threshold frequency. I spelt threshold wrong there. Should we try that again? Threshold frequency. And so our equation for that critical amount of energy is this. This symbol on the left, this phi, is called the work function. We'll be using all these equations later. So if you're watching this at home, and I really hope you're watching this, engaging with this, make a note of these because we'll be using all these equations in a bit. This work function is an amount of energy that the photons have to have. And if the photons have more than this amount of energy, or equal to this amount of energy, this threshold amount of energy, then the electrons on the surface of the metal are able to be freed. If it has less than that, then they can't be freed. And it depends on the metal. And there's various very complicated reasons why it's different for different metals, to do with lattice structures, amongst other things. So there we go. I'll just write up here a quick reminder in case you need it. The conversion from joules to electron volts we're going to be using a lot today. Remember the number was 1.6 times 10 to the negative 19 coulombs. That's the charge on the electron. And the reason why is because we tend to express this value in units of electron volts, despite the fact that if we use units of joule seconds for Planck's constant and a frequency in hertz, then this quantity ends up with a unit of joules. So we have to convert our units. And top tip for you, it's better to convert this into electron volts. Usually it's easier to work in that way around. So you can see if you're a GCSE student, what I've got is an equation you already know, an equation that you don't already know, or unless you were here last week, and it's no more complicated than the previous equation. It's just a 3-term equation. And another equation you don't yet know. But again, it's no more complicated than the others. It's just a 3-term equation. Just like the first one, it's got a Greek letter in it. But this Greek letter is the work function. It's an amount of energy that the photons have to have, above which you can get photoelectric emission. Okay. So, what's the experiment then? The experiment's to determine the work function of the metal. And the way you determine the work function of the metal is by letting the electrons leave the surface, but then stopping them again. So right now the electrons are leaving this surface, conducting around, and we're detecting current. What I can do is I can put a potential difference. I've got a little variable resistor here. Put a potential difference across that surface. If I put a potential difference across that surface, the electrons that leave now also have to fight against that potential difference. This bit up here is now negative. The metal plate is now positive. So the electrons that leave now have to try to escape an even more positive surface going towards an even more negative surface. And if they don't have enough energy, they can't make it and they fall back to this metal surface. The voltage, the potential difference that stops the photoelectrons arriving at the other side, at this other terminal, this dotted white line, is called the stopping potential. And this is here, right here, the stopping potential. So right now, if I apply 0.22 volts across here with the bottom plate positive, the top plate negative, the electrons that leave that surface, which we know could leave the surface, because look, when there's no voltage, I get a current, they don't make it to the other side. The current drops to 0. That's the stopping potential. So in our experiment, it's taken 17 minutes. I haven't actually gone on to the experiment yet. What we're going to do is we're going to measure the stopping potentials for various different wavelengths. And we're going to use that to determine the what's called the work function of the metal. Just before I move on from that, though, the electrons that do leave the surface, when there's no potential across the surface, have an amount of energy, kinetic energy. And it does vary because electrons that are deeper in the metal have to work against the resistance of the metal to get out of the metal. But in general, we can use the conservation of energy to formulate an equation. We can say that HF, the energy of a photon, that's the energy you put into the surface. We spend the work function to get out of the surface. That's just this equation we had right here, this equation here. But if I've got a frequency above the threshold frequency, then I'll have some energy left over. The energy left over is the maximum kinetic energy that the photoelectrons could have once they've left the metal surface. That's the spare change from this situation, EK max. If, however, what I do is I apply a potential so that the electrons never reach the other surface, then I end up with this term. And you'll notice that means that these two terms, let's just highlight them, these two terms are, it's a thicker highlighter pen, are equivalent in the equation. They're going to have the same value, should I say. They're not equivalent. They're going to have the same value. The maximum kinetic energy the photoelectrons have when they leave. But if I want to stop the electrons getting to the other side, I want to have it so that they have to work against this voltage, losing that energy. And if they lose exactly that amount of energy, then I've stopped those electrons reaching the other surface. The definition of potential difference was the work done per unit charge. And therefore, a charge multiplied by a voltage is an amount of energy, which is what we've got here. The charge on the electron, because that's the particle that's moving across that potential difference, multiplied by what that potential difference is the amount of energy. Okay, let's do the practical, shall we? So I'm going to need a blank spreadsheet, and I'm going to need my practical open, and we're going to get some results. We're going to very quickly analyze them. I don't know if this is going to work, and that'll leave us enough time at the end. And what I want you to do, if you're playing along at home, is perhaps take down some of these results and try it yourself later. I don't think it's going to be sensible for you to have various windows open on a computer, but try it again later. So what I'm going to do is I'm going to record the wavelength in nanometers of the electromagnetic radiation that is arriving at the surface. I really hope you can see that text. And then I'm going to record the stopping potential in volts. Remember, that's the potential difference across that surface that stops those photoelectrons completing the circuit. And we're going to start with 580 nanometers. Let's just fiddle with this and see what the stopping potential is. Okay, I mean, I'm going to make that 0.2. That's close enough. Switch up the color. Let's go with yellow. So this is now 550 nanometers. That's smaller wavelength, therefore bigger frequency. Okay, let's step up the potential. Oh, didn't have to step up very far. Okay, I'm going to make that 0.36. Fine. Let's go up again. You can do the practical pretty quickly virtually. When you're doing it for real, you end up fiddling with a little dial. I'm going to switch the filters out, but actually it doesn't take that long. Okay, I mean, I've still got the same stopping potential there, so maybe 0.36 was a bit on the high side for the previous example, but okay, I'm going to put 0.36 again. I might go back and check the yellow one, I think. Move the dial a bit too far. 0.30. There we are. Let's change that to 0.30. Of course, what you could do is do multiple recordings. Do repeats. 530 I've done. 510. This practical is not a required practical A-level, which I think is a real shame. It feels like it should be. It's not difficult to do. The problem is you need to have the apparatus. You need to have a photo cell, or you need to have a thin layer of one of these metals. The problem is the metals with work functions low enough for you to use these sorts of colors. They can be quite reactive. I'll show you in a second. I'll show you the list. So let's turn up the potential. If you have any questions while I'm doing this, just ask. I'm going through what's probably about 4 lessons worth of work very, very quickly. So if you don't follow it, then, and you're a GCSE student, don't beat yourself up. This is what you've got to look forward to, doing this in a lab. As long as we're allowed to. 0.89. At the moment, practicals in a lab, very, very difficult to do. Infrared. There's not going to be anything emitted with infrared. I'm not going to bother with that one. Ultraviolet. Let's try that one. 370. God, look at that. Loads. What I want to show you is this. Once the light is causing photoelectric emission, if I turn the brightness down, the current does go down. The brightness is the number of photons per second hitting this metal. And if there are more photons per second hitting the metal, there are more electrons per second leaving the metal. Current is rate of flow of charge. So more electrons per second leaving the metal, more current will be detected. So it's not to do with energy of the light, changing the light brightness. It's the intensity of the light, the number of photons per second per unit area. Okay, I'm going to make that 1.42. That'll close enough. And can I go any higher? No, that's it. Right, okay, so that's the practical done. There are my results. So how am I going to analyze them? Well, let's put this to one side for a second. Oh, it's gone. Excel. I'm just going to pin my spreadsheet to the top so I can scroll what's underneath it. And now I can write whilst looking at the spreadsheet as well. So what I've got here is the equation we had before. Energy of the photon equals the work function plus the stopping potential. Okay, fine. So the the energy of the photon equals HF. If I substitute C equals F lambda into there, I end up with HC over lambda equals phi plus EV. What I want to do is just get a variable equals a constant times, plus a constant times a variable. That's what I want. I want to get this in the form y equals mx plus c. It's kind of in that form already. I could leave it like this if I wanted to. Or I could divide through by h and c. But I'm going to leave it like this. I know it's a little bit sloppy, but I'm going to leave it in this form for now. And what I'm going to do, I'm going to plot on the y-axis this thing, on the x-axis this thing. That's the stopping potential. Maybe I should put a subscript s on the bottom of this. And then what I should get is this thing, which will be my gradient, the charge of the electron, maybe. And this thing, which is the y-intercept. There are different ways of doing this practical, but that's what I'm going to go with. I'm going to see if this works. It should work. So let's first of all get our x-axis. That's the potential. I've already got the potential sorted, the stopping potential. Got that. So now let's do the y-axis. So the y-axis is going to be equal to Planck's constant, 6.63 times 10 to the minus 34, multiplied by speed of light, so that's 3. Give myself a bit more room. Times, so 3E08. So this notation here, if you're not familiar with it, we will be using today. The E means times 10 to the power of. And then I'm going to divide that by the wavelength. Now you'll notice the wavelength is in nanometers. So I need that in meters. So that's divided by 1E minus 9. Times by, should I say? Divided by? Because I put it in brackets. Times by. Okay, so there's my energy. That energy is in joules. If I make that energy in electron volts, then this will be in electron volts, and this will be in electron volts. And as this is already volts, the gradient should end up being, well, I guess just, well, we'll find out, 1 maybe. So let's divide that by the charge of the electron. So that's 1.6 E minus 19. See how I get on with this. Okay, they're my photon energies in electron volts. And now the tricky bit is plotting the graph I want, forcing electron to do what I want. So I want the stopping potential on the x-axis. Let's see if it does what I want it to do. Stopping potential on the x-axis. Energy of the photon on the... Is that the energy of the photon? HC over lambda, yeah, on the y-axis. We get a straight line, that's reassuring. If I draw a trend line, is it a straight line? It's pretty good. It's not bad. And now if I extrapolate that line back, and actually I can cheat with this because I could just go into format trend line and say, show me what the equation is. There it is. So the gradient should have been 1. It's come out at 0.9954. Okay, that's not bad. 2 significant figures, that's 1. And the y-intercept is my work function, which was in electron volts, 1.97 electron volts. Mission accomplished. And I could do that again with the other metals. Now, does this let me test and see whether I got it right? No, it just allows me to show a graph and all this sort of thing. It doesn't allow me to test it and see whether I'm right or not. But look, I've got 1.97 electron volts. I have here a list. Cancel that for a second. I have here a list of the work functions, and I can look them up. And this thing here is off the top of this chart. It's very, very small work function indeed. But I think it should be 1.97. 1.97. So this is probably some sort of cesium. Cesium piece of metal that I'm shining photons onto. Crazy. Right, if there are any questions, now's the time to ask. Chuck it into the chat. Otherwise, we're going to get cracking with some questions of my own to see whether you followed those equations, understand how those equations relate to each other, and can use them. No questions. Okay, well then what I'm going to do is I'm going to hit F9 on my keyboard. This is how the drills work. If I hit F9, I get new questions. Hit F9, I get new questions. It'll be the intercept. Wombat. If you look at the way I've written the equation, this is in the form y equals mx plus c. If I plot this on the y-axis, plot this on the x-axis, this will be the gradient, and this will be the intercept. And that's exactly what I did. Now, why is the gradient coming in at 1? Because I chose to use the unit of electron volts as my energy. So electron volts is unit of energy. So it's per unit charge. And so my unit of charge is the charge on the electron. But the gradient is the unit of charge, which was the electron. Probably made it more complicated than it needed to. I should have just done it in SI units, but there we go. I did it. It's done. I have to make our peace with that. So that should be on top. There we go. Right, so here's the questions. The gradient was the charge on the electron. It's Pink Dolphin. The gradient was the unit of charge. EV is the amount of energy, because voltage is the work done, the amount of energy per unit charge. And I just set my unit of charge as the electron. So the gradient was just the electron, 1. If I'd done everything in joules instead, the gradient would have come out as 1.6 times 10 to the minus 19. But I did it all in electron volts, so the gradient came out as 1. Or near enough 1. I'd be worried if it came out exactly right. Yeah, it's not easy. It's not easy stuff. But okay, even GCSE students can now get in on this, on these questions. Just realised when I was projecting this before, I think I had a white block that was blocking part of the screen off. That's hiding the answers. But hopefully that was okay. Hopefully it didn't cause too much of a problem. So 5 questions. Here's what I want you to do. I want you to chuck into Spiral your answers to the first question. And then we'll see if you're right or not. Then the next one, then the next one, then the next one. We're going to get some practice. We're going to have about 25 minutes of just rigorous practice with this. Just going to move my Spiral window to the side so I can see it. 9 people are on Spiral. So if you are just tuning in or you tuned in a little bit later, here's the link. Just use whatever name you want. Doesn't really matter because I've got the names hidden, as you can see from this window here. And that way you can send your answers to me. They're all anonymous, but you can send your answers to me and I'll be able to see them and respond to them as the answers come through. And that way you can work at your pace, and I'm not putting a timer up there, which I think people didn't like. And I can work through these solutions as well if you like. That's fine, Freya. That's absolutely fine. Some answers are starting to come through. None of them are right yet, but I didn't properly test the spreadsheet. So when I go through the answers, it might turn out that one of yours is right. Should we go through the first one together, just as a starting point? Let's just take a screenshot of the first one and go through that together. Scroll, scroll, scroll. Okay, now remember with these, what we're looking at is the conservation of energy. That's all this is conservation of energy. Energy in equals energy out. So what's the frequency in hertz of the incident radiation? Fine. I'm just going to write my equation down here. HF. I've got my frequency here in hertz, so that's what I want. When the work function of the element, so I've been given the work function, that's good. Maximum kinetic energy. So the equation I'm using is this one. EK max is the maximum kinetic energy. E subscript K max. So there's no stopping potential in this question. But remember what I said, the stopping potential is equal to EK max. Sorry, not the stopping potential is equal to. The stopping potential multiplied by the charge on the electron is equal to the EK max. That term is either the energy the electrons have when they leave, or the energy that you need to rob from them, take away from them to stop them getting to the other side. So this is the equation. Now I'm going to start plugging my numbers in. So I'm going to say, and I'm going to do it numerically rather than symbolically to start with. Mainly, there's two reasons for that. One, GCSE students sometimes find it easier to work this way. But secondly, if you're an A-level student, minus 34, if you're an A-level student, then this is the way things will often appear on mark schemes. More often than not, things will be numerical on mark schemes rather than algebraic. But, you know, it doesn't really matter. We're after frequency equals, now, work function. 4.32 electron volts plus EK max 3.498 electron volts. But that's electron volts. The equation on the left only works in joules. This equation, H, is in units of joule seconds. So this only works in joules. So I've got to convert my energy on the right-hand side into joules. And we did that last time. It was a tricky, challenging thing to do, converting units into joules. If you, hang on, let me get rid of that white bar that's covering the answers. There we go. It's a tricky, challenging thing to do if you've never done it before. But remember, 1.6 times 10 to the minus 19 joules per electron volt. So if I times the amount of electron volts I've got by that, that gives me the answer in joules. Now I can plug that into my calculator, or I can do it all in one in a second. So I'm going to divide through my equation by the Planck's constant, which was 6.6, I hope no one corrected me, 6.63 times 10 to the negative 34. Use a number enough times, eventually it goes in. And that will be my answer. So I'm going to grab my calculator. It's going to have a quick look on Spiral and see who else has got answers coming in for that. A few answers coming in. Some of them match what I've got on my spreadsheet, which is reassuring, but a lot of them don't. So first of all, add those together, then 1.6E19 minus times, and then 6.63E34 minus divide. Okay, that's what my spreadsheet was saying as well. So I can now go through and mark some of these correct. I can write the answer in here anyway. So that was 1.8, let's call it 1.89, let's round it, times 10 to the power of 15 hertz. Does that fit on the screen there? I think that should fit on the screen. So look, yeah. Okay, and you could write that with the E instead of the times 10 to the power of. So you could write that as 1.89 E15 hertz if you wanted to, but that's not something I'd do in exams. That's just a language that spreadsheets seem to understand a bit more. So let's just have a look and see if that's what the answer says on my little spreadsheet. And ta-da! Pretty happy with that. That worked well. Okay, so if you get cracking with question 2 then, I think Spiral is open, ready to go. And again, I'm happy to go through every single one as I need to. No, not at all, Pranav. If the answer's, if it says in hertz, then you wouldn't need to bother. Question 2, it's got something interesting about it. So let's see what your answers look like as they come in. And then we'll go through a solution. Pranav, is that a typo in your answer? Ah, Wombat, that is the trick, isn't it? Here's the thing. If the stopping potential were 2 volts, then the amount of energy that corresponds to is 2 electron volts. If the stopping potential is 5 volts, then the energy is 5 electron volts. The work done per unit charge multiplied by the unit of charge is the work done, the amount of energy transferred. And that's why electron volts is such a powerful unit. Because what we're saying is if I move an electron across a potential difference of 2 volts, it picks up 2 electron volts of energy. And if I multiplied that by the charge on the electron, I'd get the amount of energy in joules. And it's up to you to decide whether you want to work in joules or whether you want to work in electron volts. I would do the conversion right near the end, to be honest with you. But we'll see. We'll go through the answer together. Yep, so I'm getting some comments saying that this is really hard. Yeah, this is hard. I'm going to put this into perspective. This is the sort of topic that would appear in an A-level, in the first year of your A-level at about November time. So, okay, that's okay, Pranav. So if you imagine you're doing your Someone's put a negative power when it's actually a positive power there, so you might want to just go back and check that. Yeah, so if you can imagine, you've been studying A-level physics. You've spent 5, 6, 7, 8 weeks. 8 weeks on all of particle physics, not just a quick bish-bash couple of hours. You've had one-to-one time with your teacher, sat there going through, having homework marked and checked, whilst at the same time you're improving your mathematics skills, because I strongly recommend A-level students take A-level mathematics as well as physics. And then you get these sorts of questions, and they're much more straightforward, just thinking, oh, that's an equation, I'll just plug these numbers in. But if you're a GCSE student, then maths still seems like a bolt-on. Well, let me tell you something. The 3 knowledges. My students have heard me talk about the 3 knowledges before, my students at school, and if you've never heard me talk about the 3 knowledges, you're in for a treat now. The 3 knowledges are the 3 aspects of physics at GCSE and at A-level that if you can crack them, you will get an A star at A-level, you will get a grade 9 at GCSE. It will happen. And they are mathematical skills, being competent in mathematics, knowing the equations, being able to plug the numbers in the right places and getting the right answers, knowing which numbers to pull out of the question, just mathematical skills. And the good thing about them is you can practice them. There are things like my drill spreadsheets, or you can go on the Isaac Physics website, quick plug for Isaac Physics. If you go on the Isaac Physics website, loads of questions you can do where you get the answers, so you can practice and develop those mathematics skills. The second of the 3 knowledges is the linguistic side of things. Physics is its own language. It has technical vocabulary that you need to master. Now, the mathematics side is about 50% of the course at GCSE, a little bit less perhaps at A-level, but about 50% of the course. The linguistic side of things is about 30%. So it's not as important, but it's still jolly important. And I joke with my students saying, all you've got to do at GCSE level is learn 23 equations and 414 definitions. Which sounds mental, isn't it? 414 definitions to memorize. But it's not that hard, because most of them you already know. You're picking up the language of physics every time you watch a physics video on YouTube, every time you read a book, every time you attend a lesson, every time you work through some questions. You're picking up this language. Things like the word power has a particular meaning. The word specific has a particular meaning in physics, and you pick those up as you work through physics problems. The third of the 3 knowledges is practical skills. The practical skills is how you apply, well, like we did today. We looked at an equation, we thought, well, let's do an experiment. We did an experiment, we pulled the data off it, we analysed the data with a graph, we made sense of it. We knew whether we had to find the gradient or the intercept by looking at the equation. Yeah, Jackson, specific means per unit mass. It's completely different to the English word specific. Specific means per unit mass. Specific charge is charge per unit mass. Specific heat capacity is heat capacity per unit mass, as opposed to a molar heat capacity. So yeah, the word specific has a particular meaning. So the practical skills is about 20% of your paper. It means that you can get probably a grade 7 at GCSE level, or maybe a grade C at A level, just with the mathematics, with nothing else. You can get an okay grade, a good grade, with just the mathematics. The linguistic side and the practical side, that's the cherry on the cake. That's the bit that takes you through to the higher grades. And so my recommendation is with these things, with these drills, just do them and do them and do them and do them until you get the right answers. So let's just go through question 2 together. And then you can have a go at question 3. So hopefully this is going to work. I can turn off my answer covering bit there. Scroll, scroll, scroll. And I've met A-level students who really enjoyed physics at GCSE level, but did not appreciate just how much mathematics there was, because at GCSE level, the maths is just 3-term equations. And at A level, all of a sudden, it's just, well, we'll just use conservation of energy. That's not an equation. And I see it on Facebook, on forums, students saying, asking for help with certain questions. And I'll say, what's the equation for this? And it leaves me scratching my head thinking, I don't know. What is the equation? There isn't an equation for that. You just do physics. You just apply your fundamental principles to that problem. It's not about finding the right equation. It's about using mathematics as a tool. So here we've got the same thing we had before, the energy of the photon. That's what we put into the metal surface. We spend the work function. So whatever we put in, we get out the work function. That's what we spend to get the electrons out of the metal surface. But also, we're now looking at stopping potential in this question. So we're also going to spend this amount to stop the electrons. This stopping potential here, Vs. So let's go ahead and plug our numbers in. 6.63 times 10 to the negative 34. This is a bit that we take for granted as physicists, that we can do this sort of thing. We want the frequency. The work function is given to us in electron volts, and that's going to be plus some stopping potential. Well, what's the energy in electron volts that an electron spends moving across a potential difference of 1.887 electron volts? 1.887 volts. I've kind of ruined it there. 1.887 electron volts. That's now, I think, quite straightforward to solve. We just need to turn the electron volts into joules again, because remember, this part here is joule seconds. That's the unit of Planck's constant, joule seconds. So we need to multiply this by 1.6 times 10 to the minus 19 first. Then tapper, tapper, tapper on our calculator. GCSE students don't get a lot of practice with this. They don't, because they use three-term equations, and some places use formula triangles. If you find someone online using formula triangles, switch it off. Don't use it. That's a bad habit. They're doing you more damage than good. Bad physics. Oh, I need to stop. Watch my rant about it. Don't use formula triangles. They're a crutch, which is going to damage your progress in physics. Absolutely. The thing is, well, Wombat, do you go to my school? Because if you do, then you will know that there are posters in every lab banning formula triangles, every physics lab. Lex. Right. Jackson, they are bad because they are a crutch and they don't teach you basic algebra and mathematical intuition, which once you've got it, questions like this you can solve without really thinking about it. It really is straightforward. Lex, your science teacher is infatuated with them. I know chemists in my school love them. Some of them, some don't. I know the maths department cannot stand the fact that in chemistry they use them. There was a study done, I can't remember who it was done by or when, but I'm vaguely remembering it now. But apparently people learn a bit of algebra in year 7. By year 8 they've forgotten it. So they have to learn it again and again and again. But they don't teach it all the time in mathematics because the curriculum has to include geometry and probability and I don't know what else. So students, they come back to algebra in year 10 and go, I can't do it. And if they're using magic triangles and covering things up, they're never going to grasp algebra. But if they use it every day as part of their physics and chemistry, and maybe biology, I don't know how much math there is in biology, counting sheep or something, but if they do it, if they use algebra every single day, then it becomes second nature. It's not an energy. Yep, so let me throw some units in here, Pranav, and I'll show you why. Let's take it back a step. Let's throw some units in here. This is joule seconds multiplied by some frequency, which will be in hertz, equals. Now, this stopping potential here, 4.36, sorry, this stopping potential, this work function here is in electron volts. The energy, the work done in moving across a potential difference is equal to this. The charge is equal to the charge on the electron. It's the electron that's moving across that gap. Okay. So what I've actually got here is an amount of energy equals to charge, which is E coulombs, multiplied by a voltage, which is 1.887 volts. Let's rearrange this. Oops, I'm getting to the edge of the screen. I think it just fit. Can you see what I've done there? It's really clever. The voltage here is 1.887 volts. 1.887 volts. The charge on the electron is in coulombs, and I'm just going to keep that as E coulombs. E coulombs multiplied by 1.887 volts is 1.887 electron volts. That's what the unit electron volts allows us to do. Yeah, it's brilliant, isn't it? So now I can just type in 1.887 electron volts, but then I have to multiply that by 1.6 times 10 to the minus 19 joules per electron volt, allowing me to cancel all the electron volts. And then, of course, divide through by Planck's constant, and you end up with an answer equal to... I'm just going to check Spiral and see if anyone's added anything since. A lot of people getting the right answer there. A lot of people getting the right answer. That is promising. Yeah, equal to... Load up my spreadsheet. Too many windows. Oops, just showing all the answers. There we go. Okay, I did show all the answers, and I don't want to ruin it. So let's get... you might have already started it. Well, we carry on. I'll use the same questions. So if we have a go at question 3 now. Question 3. It's got an extra layer of difficulty thrown on top. And then chuck your answer into Spiral. And I know it's difficult. If you're a GCSE student, I know it's difficult, but it is good practice with algebra. As you can see, we've got A-level students. In the chat, you can see A-level students who make mistakes with this algebra as well. So please don't be put off by it. Some of you are lightning fast. And they're lightning fast, and I know these students. They're lightning fast, and they've been studying A-level since September. And yet they can probably, without even writing anything down, just grab their calculators. Bad practice, you should write it down. But they can just grab their calculator, tappa, 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 tappa. All the algebra is in their head because it's second nature. There will be students who are watching this who are thinking, but I don't want to do A-level physics. I just want to do GCSE and then move on with my life. In my experience, an awful lot of students never plan to do A-level physics and then end up taking it and then end up loving it because it's so different to GCSE level. They take it as maybe their 4th A-level, or they think, well, I was all right at GCSE, I'll give it a go. They take it with their eyes open, jumping in with both feet, they can do well. Let's have a look at some of these answers on Spiral. Yeah. There's one here. It's the last significant figure is wrong. And I wonder if that's just because my spreadsheet rounded it wrong. So I'm going to quickly work through question 3 just on my calculator. I'm not going to write anything down and just see whether the answer of that last significant figure is wrong or whether it's actually right and everyone else is wrong. So let's do this. 2.5, 11.95, 1.6E19 minus, divide through by Planck's constant, 6.63E34 minus. It's going to be frequency, reciprocal of that multiplied by 3E8. Yeah, no, I think that last digit was wrong. I'm not sure what's happened there. Somebody put 87 nanometers. It's not 87 nanometers. One person, I think, has given me the frequency, but careful, it's asking for the wavelength. One person's got an answer that's quite wrong. No, let's go through question 3. Yeah, rapid fire question 3. Oh, okay, that's good. The person who put 87 has just said that they misread it and it was actually 86. That's fine. That's great. So the answer is 86 nanometers. Let's just rapid fire the answer. Just going to check and see whether my little white bar is blocking off the part of my working. No, it should be okay as long as I keep my pen to the left of the screen. So again, HF is the energy of the photon equals phi, that's the work function, plus, well, this time we're looking at the stopping potential. So this is EVS. You're never going to get stopping potential and EK max at the same time. You're not going to get that. So we're after the wavelength. So that means we need HC over lambda. I've substituted in there the equation C equals F lambda plus EVS. So I want lambda is going to equal, and again, if you are getting fluent with algebra, you can, I mean, how are you going to do that in a formula triangle? You can't. Don't use formula triangles. There are GCSE equations that formula triangles will trip you up. But be careful, because this is in the wrong unit. So I need to times that by 1.6 times 10 to the minus 19. So I plug my numbers into that. Just check you're working. Plug my numbers into that. 6.63 times 10 to the negative 34 joule seconds multiplied by 3 times 10 to the 8 meters per second. Then it's 11.95 plus, I've done this in the wrong order, it doesn't matter, 2.5 times by 1.6 times 10 to the minus 19. And it gives you 8.6 times 10 to the negative 8, which is 86 nanometers. Okay. So now the answer to question 4. How much time have I got? Oh, that's the end of the time. That's the end of the time. I'm really interested in seeing what everyone else got for the other questions, but we're out of time. Let's have a look. Yeah, so that's right. I think you queued them all up in advance, hadn't you? The individual who I've just marked correct. I think they already put loads of answers. I've already worked them all out. That's good. Right, what I'll do then, I will show you all of the answers to this set. You can check all those. Now, what are you going to do next? That's the question. Because if you're a GCSE student, you might think, oh, well, I don't need to do this. And that's fine. But if algebra is the thing that you think you need help with, then there are GCSE drill spreadsheets. Let me show you. If I go to, let's load this up. And let's go for, not full screen. Let's go with big presentation. There we are. Let's hide this. So if you go to Facebook, for example, I'm just going to make sure that I'm on the right Facebook page before I move it over. Yep. So if you go to Facebook like this, you'll find me on Facebook. I'm blocking off the YouTube chat there, but we don't need the YouTube chat right now. Let's hide that. There we are. you'll find a post pinned near the top that says something like information and links. If you click there, you'll see there's a group that's called Facebook Group for Regular Participants. If you click that link, it will take you to this group. And in this group, there is a tab somewhere called Files at the top. If you click Files, you'll find all these drill spreadsheets. If you're a GCSE student and you're finding the algebra a little bit challenging, then download the GCSE Physics formula drill and you can practice. And you can go again and again and again and again, generating question after question after question to make sure you can do all of this stuff instinctively without having to think too much about it. If you are an A-level student, you'll find there's loads. There's loads of drills here. And I haven't yet, but I'm going to, when I finish today, I'm going to upload this drill spreadsheet that we've been working on today. I will upload this where you've got the questions here. You press F9, you get a different set of questions. You work through those questions, and then you click answers, and there are the answers. And you click F9, you get a different set of questions. And you click F9, a different set of questions, and so on. And if you're interested, they're the metals corresponding to the different work functions. And there are all sorts of drills in there. There's a formula drill as well. It's quite popular. You can use those for free. If you're a regular participant, you can just go on that Facebook group. You can download them for free. The other thing I wanted to show you is the, here it is the YouTube channel. So if you've not subscribed to this, then you should definitely be thinking about clicking the subscribe link and then, you know, dinging the bell. Because... oh, I feel shame. Because there's loads of videos. I've been starting to upload more and more videos, not just the tutorials, to try and support the tutorials a bit. And here under playlists, you'll see they're all grouped by topic. So if you're an A-level student, you might enjoy the calculus playlist, which I'm trying to see and I can't see it on the screen. It's on there somewhere. Sort by created playlist. I don't even know where it is. I'm not looking for it. If you type calculus and search for calculus, you'll find it then as well. There's also this one here, derivations of physics equations. That's a good one. And I'm going to keep adding to that. There's particle physics. That's a 12-part series on particles. There it is, Introduction to Calculus, if you're an A-level student, and so on. So that's worth looking at. But if you want a slightly easier way to search for topics, if you go to the website, physicswithkeith.com, and here's the website. If you click on videos, you'll see I tried to keep this updated by topic as well, where the tutorials are included here. Sometimes they're a bit naff, especially the early tutorials. I didn't know what I was doing. I still don't. But that's all there as well. So the resources are there. And if you get stuck, just ask. What I need from you lot, which would be a tremendous help, is to know whether or not... let's get this YouTube chat thing loaded up again so I can see it. No, it's the way it works, Wombat. I've just seen your comment there. The issue might be if you're calculating things backwards, and it's not your fault, it's the way it works. So certain numbers are generated randomly, and then they plug it into an equation that then picks another number. But sometimes it asks you a question where it gives you the calculated number, which it then has to round, and asks you to calculate one of the numbers that was randomly generated. And you might end up with that being one significant figure out because of having to round the final calculation and then giving you that number. So sometimes there is a rounding error on that. I can fix it, but it is a big task to do that. It means doing every single rearrangement separately. I'm not motivated to do that. Freya says she likes the astronomy ones. Yeah, exactly. Yeah, I'm moving on to aided observations on GCSE astronomy next. In hindsight, this order of the specification wasn't the best order, actually, for me to work through those videos, but we're on track anyway. And I think that's all I needed to say. Oh, yes, what I need from you. It's little things. If you could share this with people, maybe it's people in your school, people who you know who are, you might be a homeschool student and you know other families that are as well. Share this with them if you find it helpful. If you don't find it helpful, let me know why so I can make it more helpful. And it's other things like the sound. I'm always obsessed with the sound quality. How does it sound? Is it coming through clearly enough? Is the pace too fast, too slow, and all this sort of thing. So help me out, give me some feedback. I'd be very, very grateful. Other than that, I need to load up my PowerPoint because I just want to show the last slide, as is customary. So here we go. Next session is on, thanks Wombat, next session is on radioactivity. That's going to be starting at GCSE level. Not going to go too far. More radioactivity will be A level, but I've neglected GCSE for a little while. So we're going to do GCSE level radioactivity next session. So that's usual Saturday, try again, Sunday, 10 a.m. Tune in and I will see you then. It's 11 minutes past. I really overran. My sincere apologies. Enjoy your Sunday. I'll see you next week.